Welcome to Robotics 1. In today's class, we are going to talk about differential equations, dynamics, and control of robots. We have looked at kinematics. When we looked at kinematics, we ignored the mass and the inertia effects. Now, in today's lesson, what I want to do is I want to derive differential equation of motion solve it, and then plot. Now we will start with a very simple robot that we have already looked at, and this robot is an R parallel to R robot. So you have this first revolute joint, you have this second revolute joint, and then you have an end effector. So if you remember, we solved this robot multiple times, multiple ways, but in today's class, what we are going to do is we are going to add some masses. So I'm going to say that this robot can be approximated as two mass robots, wherein M1 is the mass located at the frame 1. This is the frame 0, and M2 is the mass located at frame 2. So let's start with the first step, setting up the coordinate frame. This is going to be my Z0, X0, and I would have Y0. Then I would have Z1, X1, Y1. And please note the rules that we talked about are satisfied. So Z2, X2, and Y2. If you look at the top view, this robot is a simple two-link robot, wherein link number 1 is shown like this. This angle could be θ1. And then you have this link number 2. This is M2. And this angle is θ2. Then the lengths are, again, this is A1. This is A2. Then you have A3. And this is A4. So the assumption is M1 and M2 are the masses. What does that mean? It means even though there is hinge at the X0, Y0, Z0, that hinge is pretty much massless. So everything else is massless. And the only mass that is approximated at the frame 1, X1, Y1, Z1. And the second mass is at frame 2, X2, Y2, and Z2. We solved this problem multiple ways. We actually derived the positions of masses using homogeneous transformation. We also derived these positions using simple trigonometry. So this is A2 cosine θ1. This distance is A2 sine θ1. Then this distance is A4 sine 1 plus theta 2. And this distance that we shown over here, which is, if I were to draw over here, this is A4 cosine theta 1 plus theta 2. Now, the important part here is we are trying to solve the differential equations. So from all this kinematic diagram, all this setup, I need to find out a few things. First, I need to find out the position of mass M1. So I'm gonna call this Px M1, which is position of mass M1, Py M1, and Pz M1. This is all I need from my kinematic analysis. Similarly, I need to know Px M2, Py M2, and Pz M2. Once again, what is Px M1, Py M1, Pz M1? Is the position of mass M1 with respect to the zeroth coordinate frame. Zeroth coordinate frame is the fixed coordinate frame, inertial coordinate frame, it does not change. So I need to find out the location or the position of mass M1 with respect to this frame. I need to find out the position of mass M2 with respect to this frame. And it can be determined if you look at what we have here, I can write very easily Px M1 is, and I need to write this down. This is X naught, this is Y naught, Z is coming towards you. So Px M1 is A2 cosine theta 1, Py M1 is A2 sine theta 1, and Pz M1 is A1. Are you with me so far? Similarly, Px M2 can be written as A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. And we have done this a lot. A2 sine theta 1 plus A2 sine theta 1 plus theta 2. Last but not least, Pz M2 is A1 plus A3. A1, yeah, A4, correct. A4, 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 A4 sine theta 1, A4, A1 plus A3. Everyone understood this? Now, remember, what we need to do is we have to use the Lagrangian. Lagrangian is given by L. L is nothing but T minus V, where T is the kinetic energy and V is the potential energy.
So it will be A2, right? And the first one A2 cos theta 1 plus A4 cos theta. And in the
correct.
EYM2 it will be
Correct,
A2
got it.
sin theta 1 and then A4.
Okay. Anything else? Okay, now we are on the same page. So T is equal to kinetic energy, V is equal to potential energy. To find kinetic energy, I need to find out the velocity of the mass. And since there are position in X, position in Y, position in Z, I need to find out Px M1 dot, which I'm gonna call as Vx M1, which is nothing but A2 minus sine theta 1 dot. I can find out Py dot M1, which is Vy M1 is equal to A2 cosine theta 1 dot. I had to use the UV rule because theta 1 depends upon time. The derivative is with respect to time. So derivative of cosine theta 1 with respect to theta 1, which is minus sine theta 1, and derivative of theta 1 with respect to time, which is theta 1 dot. Everyone clear? Now this Pz dot M1 is equal to 0. Do you agree with me? Now I can repeat the exact same process for Px M1, Px M2, and Pz M2. We can do that by hand, or better yet, just use MATLAB. So the idea is, what I need to do is, I need to find out from these expressions Px dot M2, which is nothing but Vx M2. And there will be an expression here that we can find out, but I want to use MATLAB to do that. Then Py dot M2, Vy M2, and you are going to get an expression, and Pz dot M2, which I can write, which is Vz M2 is equal to 0. So first and foremost, if you want to solve the dynamic problem or dynamics problem, you need to find out the positions of the masses, where those masses are located. We are going to start an easy problem. In this particular problem, everything else is massless, except there is mass M1 and there is mass M2. M1 is conveniently located where the frame 1 is X1, Y1, Z1, and M2 is located where the frame 2 is, which is X2, Y2, and Z2. Okay, everything else is massless. So right now I just have two masses, and if you look at the top view, this kind of looks like a compound pendulum, wherein basically a double pendulum, wherein this rod is massless. You have just one mass here. The second link is massless, and you have the mass where the end effector is. Everyone understood this? So I've derived these equations purely from geometry. But if you follow the process that we have studied, what would you do? First, you will formulate you will draw the kinematic diagram. Then you will assign the coordinate system. Then you would find the rotation matrices, and then you will find out the homogeneous transformations. Everyone remember? So 0h1 for this guy is going to be cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1. Then you are going to have 0, 0, 0, 0, 1. The last row becomes 0, 0, 0. You get 1. And you have here A2 cosine theta 1, A2 sine theta 1, and then you are going to have A1. Are you with me so far? Now the next part is you are going to have 1H2, and 1H2 would have the same form. I don't have to worry about the projection matrix because note, coordinate frames are aligned, and we derived this. Remember, some time ago we derived all these equations. So this is going to become cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and this is going to become, does anyone remember?
A4 was theta 1 plus theta 2 plus A4 plus theta 2.
and then this becomes A3. Oh, N1. Everyone understood this?
Yes.
And then what we did, we found out 0H2, which is 0H1 times 1H2. Now, everyone understood we did this multiple times. Now, this guy here, you can see this is PX M1, the first guy. This is PX M1, PY M1, and PZ M1. It is the same expression that we derived over there. Everyone understood this? To find out PX M2, PY M2, and PZ M2, we need to perform this multiplication. And after this multiplication, we are going to get this big matrix wherein we are going to have 0 R2, 0, 0, 0. There will be 1, and this will be PX M2, PY M2, and PZ M2. Everyone understood this? So when you perform this multiplication, you are going to get PX M2, PY M2, PZ M2. That looks like what we have derived there. Everyone understood this? Now, what we need to do is, we need to find out the derivatives, just like we have shown over there. The second thing is, I want you to understand, is we also need to find out the potential energy. Potential energy is nothing but the energy that is stored in the spring, or energy that is because of the elevation from the datum. So potential energy, as you can see, I'm going to treat this as my datum. I'm going to treat this as my datum. Do you agree with me that mass M1 is at location A1? Do you agree with me? Mass M1 is at location A1, or distance is A1. And mass M2 is at the location which is A1 plus A3. Do you agree with me? In other words, the Z location of mass M1 is found out here, which is very important. This is the Z location of mass M1, Z position of M1. Similarly, Z position of M2 will be found here. Z position M2. Do you agree with me? So once you solve the kinematics problem, forward kinematics problem, you can get the velocities of each mass. You can get the elevation of each mass, which means now you can simply write down the equation for kinetic energy and potential energy. Everyone understood this? So what is going to be the next step? And I'm going to show it over here. Once you actually migrate onto MATLAB, it's extremely simple. It's very straightforward. But this conceptually, what this means is, first you have to solve the forward kinematics problem. You have to find out the position of each mass with respect to the inertial frame. Position of each mass with respect to inertial frame can be found out using 0H1 or 0H2 and so on and so forth. Everyone understood this? Sometimes what could happen is, rather than the mass located at the hinge, the mass could be in between. Okay, the mass, instead of mass located at the end, it could be in between. So accordingly, you will have to change the link length, and we'll work out the problems like that. In this particular problem and next problem, the masses will be at the end effector or masses will be at the frame. But the procedure remains no matter where the masses are located. What is the next step? Next step is I want to find out the kinetic energy. There are two masses. So there will be kinetic energy of mass m1. So kinetic energy of mass m1 plus kinetic energy of mass m2. Do you agree with me? Kinetic energy of mass m1 plus kinetic energy of mass m2. Now, if you look at kinetic energy is dependent on velocity. Velocity is a vector component. Velocity is a vector. I have three velocities. I have velocity in x, I have velocity in y, and I have the velocity in z. So total kinetic energy, this is extremely important, is 1/2 mv square. But since I have three velocities, I would have to sum them all. Vx square plus Vy square plus Vz square. And this all are for mass m1. Are you with me so far? Which means the expression that I have found out here, can you see this expression? This expression and this expression needs to go here. And I would just write this for my own. So 1/2 m1 Vx1 is minus a2 a yeah.
And v the whole square. So v will be substituted as vx plus vy plus vz and the whole square. So you are adding all the vectors in the and taking the representation.
The resultant vector, so it's like if you take the magnitude of x1 plus xy plus xg, you'll get under root x square x vx square plus vy square plus vz square. So that's possible.
This will become possible.
So I was asking like find the square individual components and then like
Why don't you find the vector sum and then add those, right? But even if at the end of the day, you are interested in magnitude of the velocity. In other words, you are linear algebra. You are trying to find the dot product. So I answer your question in a linear algebra term. So what you are trying to do is you have V. So you are trying to find out V square. Okay. V is a vector. So if you want to do the V square, which means you need to do V dot V. Since it's a vector, what you need to do is you will have to do V dot V transpose, which is Vx, Vy, Vz dotted with Vx, Vy, Vz, which is nothing but Vx square plus Vy square plus Vz square. Everyone understood this? Okay, so you got this. Story doesn't end there. But now I need to have 1/2 m Vx square plus Vy square plus Vz square for mass m2. And which is going to be 1/2 m2 and all this long expression that actually I did not find out. But if you were to differentiate this equation, you are going to get a long expression and that you can substitute over here. Everyone understood this? Then I have to find out the potential energy. In this robot system, there is no spring. There is only mass. So the potential energy is potential energy of mass m1 plus potential energy of mass m2. Potential energy for mass m1 is m1 g z1 plus so z and m2 g z2, which is m1 g a1 plus m2 g a1 plus a3. Everyone understood this? Now, at this point, I have the kinetic energy, I have the potential energy. Everyone understood this? I can formulate the Lagrangian. And then I would let MATLAB solve this equation and generate the solution and plot. So the procedure to solve any robot dynamic problem is this. First, draw the kinematic diagram, solve the forward kinematics problem, then find out the position of each mass where the mass is located with respect to the 0th coordinate frame, x0, y0, z0. Then find out the velocities of those masses, find the kinetic energy, find the potential energy, and then use the Lagrangian formulation or the MATLAB script to solve the equations. Yeah.
Is there a specific reason that we do not use rotational motion to write the equation of motion?
Yeah, the rotation will come next. I did not, so right now, so, okay. Now, there are two types of kinetic energies. One is the kinetic energy of translation, and second one is the kinetic energy of rotation. In this particular problem, we are ignoring the kinetic energy of rotation because it does not matter. But when we look at the case when you have a slender rod, when the mass is distributed, this expression will be kinetic energy of translation plus kinetic energy of rotation. And that actually, before I talk about kinetic energy of rotation, I need to discuss few more things. So that will come next. So first, the few problems I'm gonna just solve wherein the kinetic energy of rotation is not playing any role. Everyone understood this process? Now, how would you solve this whole thing using the MATLAB? So now I'm gonna go on to MATLAB and I will show you how this code can be written. So first and foremost, I want you to go to RS1, Robot Dynamics. Let me see. And then what you have is you have RR, Robot Dynamics. Bear with me for a second. Let me make sure RS1, I'm using the correct script. Okay. You don't have this code in that, yeah.
How does a Lagrangian equation benefit us for this program?
Okay. So Lagrangian and Hamiltonian approaches are based on energy principles. They are not dependent on the vector quantities. Right now, you are deriving the differential equations of motion purely based on the scalar quantities, which means you don't have to draw the free body diagram. You don't have to worry about how those joints are connected. I mean, if you want to solve this two pendulum problem using the Newtonian approach, we can solve it, but it will take at least 2 pages to solve. So you will have to find out, you have to separate all those joints. Then you have to find out the free body diagram. Then you have to apply the Newton's law of force is equal to mass times acceleration. Then find out the reactions, substitute those reactions back, and then finally you'll get a differential equation. It's a very tedious process. You can do it for 2 masses, 3 masses, but if you have 7, 8, 9, 10 masses, typically the Lagrangian approach is more efficient. Okay, everyone, any other questions? Okay, now what we have here is, this is the exact same thing what we solved in few classes ago. We have the RR robot. There is theta 1 and theta 2. A1, A2, A3, A4 are the links. Now you can see 0H1 matrix is shown over here, which is same as the matrix that we derived. H12 matrix is this matrix that is shown over here, which is 1H2 matrix. To solve the forward kinematics, I need to find out H02, which is simplifying H01 multiplied by H12. Everyone understood this? X position of mass M1 is the first row, 4th column in H01. Y position of mass M1 is the 2nd row, 4th column in H01. Z position of mass M1 is 3rd row, 4th column here. So essentially, I'm capturing this value, and this value. Next thing is I want to do the velocity analysis. Now please understand, and this is the trick. When you are doing the velocity analysis, you need to specify that the variable theta 1, variable theta 2 are dependent on time. So I'm specifying, since theta 1 in the parentheses t, theta 2 in the parentheses t, showing or telling MATLAB that my independent variable is time, which is t, and my dependent variable is nothing but theta 1. And I'm substituting THE1, THE2, THE1, THE2 by theta 1 and theta 2. Why do I need to do this? Because understand, at this stage, I'm going to take the derivative. And I'm going to take the derivative with respect to t. So I need to specify that theta 1 and theta 2, both these variables are dependent on t. Everyone understood this? If you don't do this, it's just you won't get the correct answers. Next step is we repeat the exact same process for mass M2. For mass M2, I need to find out the first row, 4th column in H01, H02, 2nd row, 4th column in H02, 3rd row, 4th column in H02. So I have the mass 2 location in X, mass 2 location in Y, mass 2 location in Z. Everyone understood this? The next step, I again replace theta 1 and theta 2 as a function of time in my X, Y, and Z equations for mass M2. Everyone understood this? So now I can take the derivatives, which is shown over here. Yeah.
In BZ underscore M1, we have PZ underscore new. I think M1 should be there after that. Professor, from line 27, 27, 28, 29.
27, 28, 29.
Then you haven't mentioned px underscore new underscore.
Oh, yeah, new underscore M1, correct. Yeah, I changed the code a little bit before coming here. Okay, now what I'm gonna do is I'm gonna run this code. And what I want you to observe, first let's just do it for Vx1, M1, and see if this matches the answers that we have found out. Now, can you see the velocities Vx1 or Vxm1, Vym1 and Vzm1 they are similar to the answers that we got. The only difference here, and this is extremely important, I want you to understand, is MATLAB is saying minus A2 sine theta 1 in the parenthesis t multiplied by this theta 1 t comma t, that is nothing but theta 1 dot. Everyone understood this? That is how MATLAB would give you the answer for velocity. Everyone understood this? Next thing, you have A2 cosine theta 1 t, and then you have this theta 1 t comma t. This is theta 1 dot. Now, some of you smart folks can try to figure out how can we replace this theta 1 parenthesis t comma t by another variable which is theta 1 t. Let me see how many of you are able to do that. What I usually do is when I copy this code, I replace this theta 1 t by another variable. That actually makes my life easier. But you can actually figure out a smart way wherein your entire code can run in one shot. Okay, next thing, you have to repeat the same process for mass 2. Did I make any mistakes here? Px M2 H2 Py M2 H224 Pz M2 H234, and now I have this equation. So now you will see that I got this long expression for Vxm2. This is a long expression, and I want you to note in this expression, you have minus A4 sine theta 1, theta 2 t, theta 1 plus theta 2, and you have this term, which is this theta 1 t comma t, which is nothing but theta 1 dot. Same thing, you have this theta 2 comma t, which is theta 2 dot. So you have these terms that are floating around that you can change, or you will have to change when you go to the next step. So the idea is, once you work out the problem here, you are gonna get the velocities in x, velocities in y, velocities in z for mass m1 and m2. Everyone understood this? Next step is you will go to this code, which is the example RR robot. And in this, you will notice you have the second line. I'm defining the symbolic variables. Symbolic variables are theta 1, derivative of theta 1, which is theta 1d, theta 2, derivative of theta 2, which is theta 2d, gravitational acceleration 9.81, mass m1, I'm assuming that to be 0.1, mass m2, I'm assuming that to be 0.1, L1 is nothing but A2, and L2 is nothing but A4. So L1 and L2 A1, A2, I assign them to be 0. And then what you have, you can actually specify some value of A1, A2, that doesn't matter. So you can say A1 is maybe 0.1, A2 is 0.1. And what you have here is the expression for the kinetic energy that we derived from the previous script. The only difference here is I'm replacing theta 1 parentheses t by a simple variable th1. Then I'm replacing the variable diff theta 1 parentheses t comma t parentheses complete second parentheses complete by th1d. So this entire expression is similar to the expression that we obtained from the previous script, which is the script that we just ran, our script. And then what I do is, I will just show you quickly. Kinetic energy and potential energy. Potential energy is here. Now, for sake of simplicity, I'm finding out the kinetic energy of the first mass on line number 11. I'm finding the kinetic energy of the second mass on line number 10. I'm finding out the potential energy for the first mass on line number 13. And I'm finding out the potential energy for the second mass on line number 14. So in the previous expression, what we did is solve the forward kinematics. We found out the positions. We differentiated the positions. We found out the velocity. In this expression, for Euler-Lagrange, I'm formulating the kinetic energy for each mass separately. T1 is the kinetic energy of the first mass. T2 is the kinetic energy of the second mass. Everyone understood this? V1 is the potential energy of the first mass. V2 is the potential energy for the second mass. Now, some of you may ask me, why two scripts? Ideally, you can write the whole thing in one shot. So basically, you can do the forward kinematics, you can do the velocities, you can actually formulate the expression for the kinetic energy, potential energy, solve in one shot. The only problem there is, when you are finding the velocities, you have functions of functions. So to replace the names of a function built in MATLAB function, you have to actually overload the function. So that will actually that sometimes becomes tricky. When you are welcome to try it, I did not try it because you will have to replace the diff theta 1 in the parentheses t, comma t, parentheses complete. That expression, which is a built-in MATLAB function, because diff is a MATLAB function, by another variable. So that requires overloading. But you can, if you want, you can figure it out. Next step is I need to formulate the Lagrangian, which is the kinetic energy T1 plus T2, which is the total kinetic energy T, minus V1 plus V2, which is the total potential energy. My states are theta 1, theta 1d, theta 2, theta 2d. Line number 18 should be exactly identical as line number 2, because the states are written as theta 1, theta 1d, theta 2, theta 2d. In this problem, there are no internal forces, there are no external forces, there is no damping. Now, I want you to understand, at the end of the day, when you are trying to add a controller term, what does it mean when we add a controller term? When we add a controller term, we are going to change the equations of dynamics. So you can add the controller term here and still you will be able to simulate the performance, but we'll talk about it later. In this problem, there is no control. Right now, it is like the 2 degree of freedom robot, which is in the horizontal plane, and we are trying to simulate its motion. Next step is you use Euler-Lagrange function, generate the code, and here I'm specifying some initial condition. Time span is how long do I want to integrate this equation of motion. Time span is 0 to 100 seconds. Now, 0.1, 0.2, 0.1, 0.2, these are the initial conditions. So the first one is theta 1. This is theta 1d, theta 2, and then I have theta 2d. So I have the initial position, initial velocity of joint theta 1, initial position of theta 2, initial velocity of theta 2. And then what I do is I perform the numerical integration and generate the plot. To solve, what I would do is press this run button. It will take some time. It's going to basically formulate the Euler-Lagrange equation, call the function, derive the differential equation, write those equations in a file in a first order form, use the numerical solver to numerically integrate, and finally it will give you the solution. Everyone understood this? The only step that is missing here is visualization. So what you can do is you can actually add a visualization part, just generate a URDF file based on the parameters, and then you can actually provide these values of theta 1 dot. So you will see your actual robot moving. So this is the solution of the differential equation. This is how the robot is going to move. So you have theta 1, you have theta 1 dot, you have theta 2, and you have theta 2 dot. Everyone understood this? You have theta 1, theta 1 dot, theta 2, theta 3 dot. Now it's a two pendulum system, so there is no dissipation. So you would see that you are going to have some type of a continuous motion. Everyone understood this process? Any questions? I'm going to work out one more problem. In the meanwhile, I'm going to set that problem up and start working out. But I would strongly recommend that if you have your MATLAB up and running, run this code. Make sure your results are exactly same as the results that I have shown over here. So now let me solve. Yeah. Hmm. Does it work? Try doing that and tell me, does it work or it doesn't work? Okay. Okay. The good news is now I can share two screens at the same time. Very good. Okay. So the second problem that I would like to solve is similar to the first problem, but And we have actually worked out this problem. So now what we have is we have a revolute joint. And to this revolute joint, we have a prismatic joint. So what we have is we have this prismatic joint. So we have revolute joint, and then I have this prismatic joint. And I have this end effector, which is over here. And we have solved this problem. Once again, we have to set up the coordinate frame, coordinate system. And then basically perform the forward kinematics, find out the end effector position. So in this problem, everything is massless. The only mass which is located at the end is m. So this mass is located at the end, and this mass is m kilograms. You have a revolute joint, you have a prismatic joint. If you want to see how this system looks, you can think about it like visualization. It will be something like this. You have a revolute joint, and then you are going to have a prismatic joint, and you would have this mass that is located at the end. And we can provide some distances. We can say that this distance maybe is L1. This distance, actually, let me write this down like this. This distance is D1 or D2. This distance is A1. And this is the kinematic diagram. That is the kinematic diagram, but the robot actually looks something like this. You are going to have this angle as theta, theta 1. So the two variables are theta 1 and D1. So please understand, mass M1, you can change the value of theta 1 and the position of mass M1 would be different. You can extend or contract this actuator length, which is D2, and the mass M1 would move closer to the origin, or it can move away from the origin. So what we want to do is, we want to solve this problem. And to solve this problem, we have to use again 0H1. You have to find the first homogeneous transformation. Then you have to find out 1H2. And then find out 0H2. Now in this problem, deliberately, I have not added any mass at the frame 1. So this is my frame 0. This is my frame 1. And I'm going to have my frame 2 over here. So I have not added any mass at frame 1. The entire mass is located at frame 2. So small m is the mass located at end effector. So if I want to find out Px of m, Py of m, and Pz of m, I can get those values from 0h2, 0r2, 0, 1, pxm, pym, and pzm. Do you agree with me? I'm gonna give you this distance, maybe A3. So this is gonna be A1. So I try to solve this problem. I have the rotation matrix there. I don't have any rotation matrix for 1H2 because it's purely translation. But to find out the total position for the end effector where the mass M is located, I need to perform this multiplication and find out Px at M1. So Px at M, Py at M, and Pz at M. Everyone understood this? Now, can someone tell me what would it be? Name the link. I already named them here, right? Pxm would be A1 plus D2 cosine theta 1, A1 plus D2 sine theta 1, and Pzm is going to be A3. So this is my X. This is my Y. X naught, Y naught, Z naught. Look from top. This distance, I'm saying this distance is A1. And I'm calling this distance as D2. Are you with me so far? So you would get Pxm, Pym, Pzm. Here, please note, D2 is a function of time. Theta 1 is the function of time. So when you take the derivative, you will have to take the derivative of both these terms. But we'll let MATLAB worry about that. So at the end, what I have here is I have Pxm, I have Pym, I have Pzm, and I can find out the kinetic energy of mass is 1/2 m Pxm dot square plus Pym dot square plus Pzm dot square, and this guy is actually 0 because as you can see it is constant. So this is nothing but Vx square plus Vy square. Potential energy is m times g times h, which is nothing but m times g times Pzm, which is nothing but A3. Are you with me so far? So in this problem, I have RP joint, I have a revolute joint, and I have a prismatic joint. All the mass is located at the end effector. The M is at end effector. So I found out from Hobonius transformation what is the position of the mass in X coordinate, in Y coordinate, and Z coordinate. I took the derivative to find out the velocity in X, velocity in Y, velocity in Z. And then I have the kinetic energy, I have the potential energy. Now I can use the Lagrangian script to solve the problem. Everyone understood this?
Previous consideration of two parallel revolutions. You assume M1 to be the mass of the revolute joint at the second revolute.
Correct.
And the M mass at the end effector.
Correct.
Here, why did you assume that
Just to make our lives easier. I mean, I want to make your life complex, but gradually. But okay, since we talked about complex, remember, life is complex. Why it is complex? Because it has real and imaginary components. How do you solve a complex problem? Identify the real part, identify the imaginary part. Solve real part first and worry about the imaginary part later. Remember that. So if you are worrying about the next assignment, remember, there is a real part and an imaginary part. Don't let imaginary part ruin your real part. Okay. Now what I'm going to do is, so I want you to go back to RS1. Let me see. Yeah. Please go to this RP assignment 4. RP assignment 4. And here, I want you to go to the equation, run this pendulum first. So, what you see here is velocity in X, velocity in Y. That is nothing but, I derived that by taking the derivative of position in X and position in Y. Everyone understood this? So position in X is Px is equal to A1 plus D2 cosine theta 1, which is A1 cosine theta 1 plus D2 cosine theta 1. D by dt of Px. A1 is a constant. A1 cosine becomes minus sine multiplied by derivative of theta 1 with respect to time, theta 1 dot. Now it is important. D2 is also variable. D2 depends upon time. Theta 1 depends upon time. So I have to use UV rule. So first it would be D2 dot cosine theta 1 plus D2 cosine theta 1 becomes minus sine theta 1 dot. And I want you to look at the expression that I have written over there to see if it makes sense. Py is equal to A1 plus D2 sine theta 1 d by dt of Py. This is nothing but Vx. This is nothing but Vy. You have to do the same mathematical jugglery. A1 cosine theta 1 dot plus D2 dot sine theta 1 plus D2 cosine theta 1 dot. Are you with me? You got the same expression over there. And Vz is 0. So first, right now I have two variables. I have theta 1 and D2. So I need to add the derivative of theta 1, which is theta 1d, derivative of D2, which is D2d. Everyone understood? That's line number 4. Any question? Line number 4 is theta 1 is the first angle. Theta 1d is the derivative of that angle. D2 is the displacement. D2d is the derivative of the displacement. Then I have L1, I'm just saying L1 is equal to 1 to begin with. M1 is 1, G is equal to 9.81. These are all the constants. And then what I have here is I have all those values. The only difference here is I want you to understand the way I have drawn the robot is in this configuration. Robot is in this configuration. Do you agree with me? Which means the z distance, m times g times z, is always going to be constant. It's not going to change. Everyone understood this? There, when I solve that problem, I analyze the case when this whole thing is rotated, which means what you have is you have the revolute joint, something like this, and then you have the prismatic joint. So here, the only change that you will need to make is the potential energy here is going to be M2 multiplied by whatever the value is, L1, right? M2, what the distance is, I didn't give that value here. So A2 is equal to 1. I'm just gonna give A2 is equal to 1. M2 times G times A2. So that is the only change you will have to make to solve this problem. And this is actually A2. This is A2. This is A1. And this is D2. And then you can run the code. And then it will give you the answer. Please run this code and make sure you are getting answers. Yeah. Line 16th. Okay. Let me explain the entire code once again. So line number 4 is where you define your variables. The two variables here are the angle theta 1 and the displacement d2. So angular derivative, displacement, derivative of displacement. So th1, th1d, d2 and d2d. Then L1, M1, G, all those values, those are the constants. Then Vx is nothing but the velocity expression that we derived here. Vy is the velocity expression that we derived here. Kinetic energy is 1/2 multiplied by m2 in the parentheses, x velocity square plus y velocity square. Everyone understood this? Next line, the potential energy in this configuration. Why in this configuration? Because note my z is like this, x and y. So the distance, the z distance is remaining constant. This mass is not going up or down. So this mass is only going to be in the horizontal plane. So this distance is going to be A2. So you have M2 times G times A2. That would be the potential energy. Lagrangian is the kinetic energy minus potential energy. On line number 15, these parameters are needed for Euler-Lagrange code to run. On line number 15, you specify the states theta 1, theta 1d, d2, d2d. Same thing as line number 4. internal forces, there are no internal forces. External forces, there is no load or there is no controller, so external forces are zero. Damping, there is no damping, and there are no external parameters.
So will the mass not register as an external force?
No, mass will be part of, mass is already included in two. Okay. There is no external force. External force would be like if you have an external force F of T, but there is no force, or if you have an external controller. We'll work on those little bit later, but I want you to understand that is what is the code looks like. And then you run the Euler-Lagrange, and then you will generate these plots. So these are the thing, but theta 1, derivative of theta 1, displacement d2, and derivative of displacement d2. So I'm gonna stop here, but I would encourage, I have actually worked out quite a few cases. Yes. I worked out quite a few cases wherein you have R perpendicular to R. I would encourage you to take a look at R perpendicular to R code. I also encourage you to look at the code which is in robot dynamics, which is again R perpendicular R with a slender rod, because in this all these cases we ignore the rotational kinetic energy. In next class, we are going to talk about what happens when the mass is distributed, and you have to take into account the rotational kinetic energy.
So we'll be dealing with like moment of inertia.
Yeah, moment of inertia, inertia tensor next class. Okay, I'll stop here. Yeah.